Hello, in this video we're going to be looking at how we can use the Poisson distribution to approximate the binomial distribution. Okay, and we're going to be looking at the conditions when we can use the Poisson distribution to approximate it, and we're going to show kind of why it works. Okay, so let's imagine the situation where a particular, the probability even of someone being allergic to a chemical in a factory, random chemical, random factory, is, well, 1 in 1,000. So 1 out of 1,000, which is a decimal 0.001. Okay. Now, a particular factory employs 500 people. The question we're going to be asking is, what is the probability that more than 2 people are allergic in the factory? Okay. Now, this you should recognize is actually a binomial distribution. Okay, let x be the number of people allergic. Allergic. Okay. Now that means that x is going to be modeled by a binomial distribution NP, where n is equal to 500, so we're picking people out of the 500, and the probability of success, it's not really a success if you're allergic, but is 0.01, and q is equal to 0.999. Okay. Now, this is what we did in stats 1. Okay, so using the binomial distribution, we could work out the probability that there are exactly 6 people allergic. Okay, and we'd have to use, let's see if I can do this. I think I can put equations in. We'd have to use the binomial probabilities. So if I get rid of that, if I put in probability that x is equal to 6, I'm going to need a script there. Okay, let's wait for it to do something. We'll do something that is tiny. That is ridiculous, but there we go. 500. And then if I just... That is ridiculously small. I'm not happy with that. Oh, I've made a right bloody pigs here of this. Right. 6. There we go. We multiply it by the probability of 6 people being... so it's 0.001 to the 6, and then multiply it by 0.999 to the power of, well, it's 500 minus 6, so it's 494. Okay, and we can get an answer. I'm going to do this on my calculator, so I'll sing a song. I'm not going to sing a song while I'm doing this. La-di-da-di-da. Da-da-da-da. Love a bit of statistics. Make sure I don't get this incorrect. Oh, we get a tiny probability, which is what you'd probably expect. 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. Now, what we're after, however, is not the probability that x is equal to 6, but the probability that x is larger than 2. Okay. Now we could use the tables for this. Okay, we could use the tables for this, but the tables only go up to n is 20. Remember, this is the probability that x is equal to 3 plus the probability that x is equal to 4 plus the probability, well, it's going to go all the way up to plus the probability that x is equal to 500. Okay. Alternatively, we could write this. I mean, we're never going to. That's 497 different probabilities we calculate. We're not going to do that in the exam. We could use the trick that the probability of x is larger than 2 is actually equal to 1 minus the probability that x is less than or equal to 2. Okay, so if I insert symbol there, hopefully that will come up as one of the common ones, the little river. Okay, now this particular probability we can get from the tables, but we can't get from the tables for the pure reason that n is 500. Rifter. Right, n is 500. Okay, our tables only go up to n is 20. Okay, so we've got a problem here. Okay, we've got a massive binomial distribution. How's this going to work? Now, I'm going to demonstrate this to you using Excel, because Excel's powerful enough to be able to deal with this. Okay, so what we're going to get the probability that one person person randomly chosen is allergic. So this should be quite simple. I've do the combination 500, and I'm going to link that to A2. Okay, and I'm going to multiply it by 0.001 to the power of A2, and I can introduce double brackets here, because I always go a bit crazy on the double brackets, but I don't care, because I want to get it right. Okay, and then it's 0.999, let's get this formula right, to the power of, well, it's going to be 500 minus A2. Okay, right, there's the probability is 1. I've just realised I'm just going to cut all these for a second. Go like that, because I also need to introduce 0. So hopefully that will go up to 0. Good. So we know the exact probability that there's no one out of the 500 is allergic is 0.60637. Okay. Now I can drag all of these down. I can get all of those probabilities. Okay. And you notice that they go very small very quickly, because we're dealing with quite a small probability. Look, I mean, we're dealing with tiny probabilities here. Really, it's those ones which are only significant. Okay. Now let's graph these. Okay. Let's get a little scatter graph of these. That is mental. So that's clearly select data. I'm going to edit these. I'm going to make the x values. Yep, that's fine. I'm going to make the y values. That's fine. That is absolutely fine. What's happened here, that this graph is actually fine. It's difficult to see unless I make it really, really big. We've got massive skew at the front. So this is my first way of thinking that, I mean, with all the probabilities towards the front, Poisson distribution is one where we deal with massive skew. So I'm thinking to myself, right, let's think about the Poisson distribution. Let's see if this works, okay? Let's see if we can do this with the Poisson distribution. Now, let's think about the expectation. In a Poisson distribution, the expected number of cases, I don't know why it's gone red. Weird. Actually, I do know why, but I'm not going to worry about it too much. Greek letters, lambda, the best of all the Greek letters. Okay. This lambda, our expectation for the Poisson, okay, is going to be exactly the same as the expectation for the binomial. Now, the expectation for the binomial is NP. Okay. So what that's if we're going to approximate this using the Poisson, Why is it? There we go. Okay, n is going to be 500, and we multiply it by 0.001, which is going to be equal to 0.5. Okay, we're going to expect that we have 0.5 of a person out of those 500 who are going to be allergic. Now, this is brilliant. Little grifter. Right, there we go. Lambda is 0.5. We're now going to approximate x, the number of people allergic, by a Poisson distribution, Poisson, I don't know, of 0.5. Okay, and let's just see how these compare. Okay, so let me write Poisson distribution there. I need to wrap the text to make that look nice. Right, so we're dealing with it's got a mean of 0.5, an expectation of 0.5, so it'll be exp, and it'll be minus 0.5, because it has to be minus, remember. Then it's going to be 0.5 to the power of that divided by that factorial of that. Didn't need those extra ones. Now look how close they are. Okay. Happy as Larry. They are looking very, very nice here. Look at that. They look all similar. The Poisson is a good approximation for the binomial in this case. Let's just go all the way down to, why not? We know what's going to happen. They're all going to be zero number. We get even division by, yeah, they go even beyond Excel's calculations there, but look how similar these little grifters are. Okay, they're all they're pretty much the same given to 6 decimal places. That's 5 decimal places. That's really, really good approximation. Okay. Now the beauty of this is that if we use the Poisson, which is 0.5, the probability that x is larger than 2, in fact I got it there, is equal to the probability. What? That is really grifterish, that. I don't care for it one bit. It's equal to that. Now, because we're using Poisson now, we can get these from the tables. We know that that probability we can get from the tables. That is really irritating. Okay? We can get that from the tables because I mean, I've got Excel. I could get it from Excel, but we're going to get it from the tables. If I go on Google, Google.com, which does not exist. Let's go to MEI statistical tables. There we go. Should get a PDF file here. Okay, so where are we? We get the whole lot here. Let's go. We want Poisson. Love a bit of fish. Right, we want a Poisson. Lambda is 0.5. Lambda is 0.5. So where are we dealing with? Okay, so we're dealing with these little grifters here. I want a pen. There we go. And in particular, we want that 0.2. So it's this one here, 0.9856. So it's going to be, let's get rid of the pen. This is where my computer usually breaks. 1 minus 0.98. You know, I've forgotten it. I've blinking well forgotten it. 0.9856. 98556, which is equal to the calculator tap in 0.0144. Okay, this is our answer. This is our answer. So we have used the Poisson distribution to approximate the binomial distribution, because the binomial distribution we couldn't do the calculations for it because n was too big. So the conditions, the key conditions which you need to decide whether you can use the Poisson to model the binomial is that n is large. okay, n is big, which basically says you can't use the tables. Okay. We also need the p is small. Okay. If p isn't small, what we end up with is a symmetrical distribution. The binomial will be more symmetrical. Okay. P is small ensures that the binomial is skewed positively, like the Poisson. And 3, the third condition, NP isn't too big, and we'd say less than or equal to 10. Okay, so we can use the Poisson tables. Okay, because remember, when the Poisson table, when NP, the expectation, gets too big, the Poisson will look symmetrical anyway. Okay, so I hope that's explained how we deal with approximating the binomial to the using the Poisson distribution. Brilliant.